Okay, we're going to pose a supplementary problem here. Goes beyond the capstone and shows you an important property related to the idea of scaling. And scaling is an extremely important concept in mathematics and in the application of mathematics across multiple fields. Okay, so we're going to talk about multiple scaling. Now let's assume that we have a frequency versus length graph for the pendulum, and we've determined from careful observations that the y factor is approximately 1.6. Well, y factor of 1.6 would give you p equals 0.678 or something like that, about 0.68. Well, 0.667 as opposed to 678, pretty close, is 2/3. Okay, so we're going to assume a power of 2/3 just to make it kind of nice in terms of integers and stuff. Remember, that's the square of the cube root of L there. So that our model is going to be frequency equals some number A times L to the 2/3. And A, as you should understand by now, really depends on what units you've used to observe the pendulum. Do you measure your frequency in cycles per second and cycles per minute? Do you observe your length in centimeters, inches, feet, meters? Really depends on the units you use to measure what your number for A is. Okay, well, anyhow, we have this situation and we assume all this. Now, we take some more data. We make some really long pendulums. We hang them from towers and buildings and so forth, and we measure the frequency of a 100-yard pendulum, a pendulum 100 yards long, and then we even do one for a pendulum that's 1/10 of a mile long. Okay, so we find that for a pendulum 100 yards long, our frequency is 3.2 cycles per minute. Now, if we're building a 100-yard pendulum, we probably make observations that allow us to determine this frequency to a couple more significant figures, because once we get the thing up there, we might as well go ahead and time it for an hour, let's say, and that would give us a really pretty precise measure of the frequency. Same with this one. But let's just take the simple numbers so we don't get cluttered up with a lot of numbers, and again assume that for 100 yards we observe a frequency of 3.2 cycles per minute. And for a pendulum 1/10 of a mile long, we observe a frequency of 2.3 cycles per minute. Now, we want to use each of these in turn to scale this graph. We're going to use the same scale for both data points for our frequency. So our frequency in both cases is going to be cycles per minute, or hertz, but I don't want to use that term that might not be completely familiar. I've used it before, but we'll just say cycles per minute. That's perfectly okay. If you want to remember that that's hertz, that's a useful thing to know, but not required at this point. Okay, now, so using the same scale for F, the cycles per minute scale for F, we want to label the graph according to the first data point, and then we want to label it according to the second data point. Okay, so just to get you started, just in case there's any mystery to this, to label our first data point, we just pick a point on the graph, and let's say a point about here. And that point is going to be, and notice I used the yellow chalk, let's emphasize that. That's going to correspond to this data point. Okay, so that corresponding to this data point tells you what? Tells you that 3.2 cycles per minute is here on the frequency axis, and 100 yards is here. Okay, now, having determined this data point, there's only one data point that could possibly correspond to this information. And that data point occurs with frequency equal 2/3 of a cycle per minute. So if the frequency is 2.3, not 2/3, 2.3 cycles per minute, where's that? Maybe about here. Well, you want to locate that pretty carefully and go over here and determine where 1/10 of a mile is.